The key idea of Microsound is to have an ability to represent a signal as a result of combination of arbitrary number of small chunks, small sonic chunks, usually called grains or particles. And these should be individually controllable, and we should have an ability to overlap them if we want. And you might guess, like from this basic idea, that if we have that ability, we then have to design a method to control those. I mean, when you, let's say, have 10 grains and you create something with those, it's cool, yeah. What if you have 100 or 1000 grains? 1000 grains per second, and how do you control those? This ability by itself opens up lots of design decisions, and I guess that's one of the reasons why this paradigm, while being not a new thing, is not as popular as easier graspable ideas of subtractive synthesis or even modulational synthesis. Nevertheless, it allows to enrich already existing, actually any synthesis methods, as well as to present new ones. It can be used to synthesize musical sounds with certain pitches, harmonic or noisy, as well as it allows to process incoming sound. In Supercollider we have at least two methods to work with Microsound algorithms, and I, in this first video, would like to take a look at those by working with that basic idea of reconstructing a signal from an arbitrary number of grains, and later I will take a look at individual design decisions from the musical categorization, from the musical point of view. So the first approach is based on using granular unit generators inside of the synth def. This approach is very precise timing wise, but has some limitations, some obvious limitations. Let's take a look at this example. The sound will be this. Monophonic guitar recording. We have an NDEF which has a phaser and a buffer D that is controlled by this phaser. Yeah, the first part, let's call it the first part of this NDEF. Let's take a listen what it gives us. So we now have dual mono playback of this buffer. The phaser is a unit generator that generates a linear ramp which increases at every next sample by the amount specified by rate and goes from starting point to the end point. Yeah. Buffer D then uses that thing to control or index into a table. Yeah. Index into a buffer, let's say like that. Yeah, that will be more proper. Yeah. So we have this buffer D. We use it without any interpolation. We just read the signal from memory as it is there. And the phaser goes from 0 to a number of frames that we have in in the buffer. I specify it here. No, not here. What the fuck? I specify it here. I specify it here as buff frames. Now let's take a listen at what can we do with the GrainBuf unit generator, and I will explain that thing. Looks pretty similar, yeah. So GrainBuf has a following interface. I put it here in its entirety. It uses a trigger specified here as this impulse unit generator. This unit generator has frequency control, yeah, and corresponding to that frequency it emits ones, 1 1, and then zeros, yeah. So it goes like 1 zeros, then the period specified by this t-frag ends up and another one comes up. So whenever the GrainBuf receives a trigger, it takes the current values that are on the corresponding inputs and calculates a new grain. And after the grain started, and it's important thing, it doesn't care about what are the signals here on the inputs of its parameters, yeah. So the control signals become kind of stair-stepped, yeah. So this is important thing to keep in mind. So that means that if we want a more fine-grained control change for these parameters like duration or rate, for example, we will have to raise the trigger rate, yeah, or density. Density is the parameter that's usually used because, I guess, because it applies nicely semantically both to periodic and non-periodic trigger sequences. So what we have here is the overlap parameter over t-frag that is used to control duration of grains. T-frag is the, as I mentioned, the one that is used to control trigger frequency, yeah. And by using it here, we make the duration of grains dependent on the trigger density, yeah. So if, for example, I specify overlap as 1, that will mean that the duration is equal to 1 period of the trigger generator. If I specify it as 2, that means it equals to 2 periods of trigger generator. And now the neighboring grains will start to overlap with each other. Phasor that controls here the position from which every next grain will start is normalized to the number of frames, so that a GrainBuf will receive what it wants to, the position control signal that goes from 0 to 1. Now I would like to make a null test and take a look at this overlap. It's the main parameter that I change here, basically. SND buff is the buffer that we read from. Rate is unchanged, yeah. Phasor controls the position, so it's basically the same thing that goes here to the sample player and the granulator, yeah. And env num, yeah, by the way, is the number. As you can see, basically it should be a number of the buffer which controls an envelope for the that is used for window, yeah. But here, if you specify -1, it will calculate a hand window, or probably it's just stored somewhere in the source code, and use just that. Yeah, I didn't tell you about window. Yeah, I told about it in the previous videos, but okay. When we take a chunk from memory, yeah, chunk of the signal, we want to multiply it by the window function, which is usually this type of thing. As you can see, one of the key features of it, fade in, fade out, yeah, so that we will not have discontinuities in the grain, yeah. And other features of it, well, sometimes considered from the technical point of view, so that it will not introduce a lot of changes to the signal, yeah. Because if the grain rate is high, this thing will introduce its own spectrum components, yeah. Hunting window in particularly relatively is rather clean in that regard, but it might be a percussive, for example, thing, yeah, percussive envelope, and you will definitely hear it when it comes. And in if the grain rate is higher than 20, well, this will give it spectral, periodic spectral components. So we have something like this, probably the same thing as this. Well, why? Probably this is a hand window, yeah, and there we have a hand window. So what the fuck is wrong with me? Okay. Hand window. We multiply the chunk that we take from a memory by this window, and then output that thing. We also have an interpolation, and I put I don't know for what, cubic interpolation here, but actually there should be no difference if I use cubic or not. So let's take a look. Without interpolation here, without interpolation here, just simple sample reader and a granulator. Null test. Do we have anything? I don't see anything. Is it me? What's wrong here? Okay. Nothing. Here are the controls. Let's take a look at overlap parameter. What happens if we change it? Let's go back to 2. Let's take more than 2. So, as you can see from this example, overlap equal to 2 gives us the, well, identical signal. Yeah. So this is first method that we can use to start with Microsound algorithms. And few next videos that I will do on this subject will deal with just this GrainBuf unit generator. But as you might guess, we are pretty limited here. We can change the rate of the grain, and that will mean that grains will play faster and correspondingly on the higher rate with higher pitch, yeah, or slower and lower pitch. We can play with the position, yeah. Now it's just linearly changed, and when it reaches the end, that's how this phasor works. It will start from the beginning, from this value, which is 0 here. Yeah, we can play with that as well. We can also play with the duration. That might have lots of interesting effects, and the trigger frequency. Yeah, this one, this parameter here. But we don't have an ability to play, for example, with the amplitude of the grain. We don't have this input here, not present. There are some others like T grains. I guess it, if I'm not mistaken, it has one, has the input. But what if we want to use some filters inside, or some other stuff like FFT processing inside of the grain, or anything else? We don't have this ability if we don't have corresponding unit generator that does that inside. So there is another approach which is based on specifying a grain as a synth. Yeah. So the synth will contain a definition for just one grain, and we can put anything we want inside of it. And then we will just bombard the server with the corresponding messages to generate new grains. Yeah. Now the question is, can we solve the same task as here, following that message, following that method? And what are the limitations or some specifics that we will have? So I already specified, I already calculated this envelope, and I will use it here with this line. This envelope is 1024 samples long. Yeah, and to specify a certain duration for it, because okay, if it's I have sample rate of 44.1 kilohertz with this system, and I need to calculate the corresponding duration, and by using interpolation I want to stretch that window that I have in memory, make it longer or shorter. This function, sorry, not function, this equation, let's call it like that, will solve the task. So what I do here, I specify a duration in seconds. Here it's 100 milliseconds, and then I convert that to samples, how many samples it will be, and divide it by the length of the buffer, which is 1024 samples. Yeah. And by that result I divide the 1, and that will give me the corresponding duration with this PlayBuf unit generator. So let's plot it. As you can see now it's 100 milliseconds. Yeah, I can put something like 4 here, and it will become corresponding duration. PlayBuf uses cubic interpolation inside, and it gives usually rather good results. So why not using just phaser and buffRD the same way as I do for grains generation? Because here it's same as here I used for the sample player part. Yeah, it's just here it will not play the whole sample but only a small chunk. Yeah, but the thing is PlayBuf does pretty the same thing with some limitations. This interface allows a more thorough approach. Yeah, but I don't need it, and since I don't need it, I have cubic interpolation inside. I have an ability to calculate rate. Yeah, and more than that, I have an ability to specify a done action. So when this PlayBuf will finish playing the buffer, it will free the synth. Yeah, just what I want. And the last thing that I have here is this OffsetOut thing instead of out. What it gives us is more precise, which is pretty important in this case, and basically is the main limitation of this approach, the timing precision. Without this, the out unit generator is limited by the control block length. Yeah, so you cannot get more precise, you cannot be more precise than one control block. OffsetOut will delays the signal, if I'm not mistaken. It delays the signal so that it will fit now, so that it will start, yeah, it will know, it will be outputted at the time that is, well, more or less close to what we want. I'm speaking now from the user's perspective, because I don't know the source code of that thing. And the thing is, all of this procedure is not only dependent to the source code of Supercollider and how you deal with it in SC lang part. It's also pretty dependent, as I got it, on the hardware that you use and how your driver is set up. In my case, I'm using e.t.c subsystem, so I have two different machines, and on two different machines with same setup, well, more or less same. The e.t.c is set up in the same way, and Supercollider, I've run basically the same code, and I get very different results. Well, in a sense of how close can I get to a perfect timing? Well, from subjective point of view, so that I don't hear the difference. Yeah, I'm not even talking about the perfect null test. So OffsetOut is important here. OffsetOut is important if we want to be closer to single sample precision. Another thing is this send bundle message. As you might see, I have a tdef, which is a task with proxy. Mainly I use it so that I would be faster with prototyping. Yeah, by using tdef you can change parameters on the fly, same as with enddef. Yeah, and it will just stop the previous task and start a new one, and will crossfade into each other. Yeah, that's my key reasons, but you can get even more with that, about that in later videos. Let's take a look at what I have here. So this tdef contains a function contains a function with the loop inside. In this loop I use send bundle. This is probably the cheapest method to tell the server to start a new synthesis node. Send bundle with new message. So send bundle has these two arguments. One is the latency, which is needed so that server will do what it intended to with this whole message in time. If it will not, it will post to the post window late string, yeah, the late word, which means that it cannot do that as fast as you want it to. Specifying latency as this first argument might help with that, and I use, just as I found it in the help file, this latency. So latency also specifies some latency for a server, as well as I use the same value here for this send bundle message to the server. Send bundle will tell the server the exact time at which server should do what's specified in the message. New tells the server to start a new synthesis node. Yeah, the second we can call this argument, but actually, as you can see, this is an array that is used to construct the resulting message. And I guess, no, it's not like that. Yeah, it's used to construct. That's the right word. So the second element is the name of the synth-def, and after that we can see some interesting things. They are specified in this help window, if you want to know more about that. obvious thing to want. Server command reference, you can find this in the help file. Yeah, and these are the actual messages to which SC-synth process reacts. This is how it operates. Yeah, we can send them from any language, however we want. It will react to them and do the stuff that it usually does with those synth objects and so on. So snew, create a new synth. Yeah, and then go the elements of this array in a corresponding order. So it has then a synth ID that we want to assign to this synthesis node. Later we can communicate with the server and tell it what to do with that one by specifying this ID. Add action, how to add it, add to head, add to tail, and so on. And the target ID, if we want to specify a group for that. And after that we'll go corresponding synth args, yeah, control signals and their values. Name, then value, name and value. So what I do here, I specify Interonset, because now we have kind of to simulate this thing, yeah, this thing. We have impulse here, which is periodic signal, and when it emits 1, this guy generates a grain, yeah. So the period of that impulse signal is what I implement here, what I use here. I specify it as an Interonset value in seconds, and then use it to wait between the new bundle with this snew message. Yeah. I also use this Interonset to specify a duration, so you can guess that this will mean that overlap will be equal to 2. It will be same as overlap equals to 2 in this case. Yeah, in this case. And I also have to now specify a position for every new grain in the same manner as I did it previously with phasor. So what I do is I'll calculate the Interonset time, that period, in samples, multiply it by the counter, loop counter argument. This argument will grow by 1 every iteration, and then I use modular, this modular operator, with the number of frames in the buffer, which does following. When this part will grow to a number of frames in the buffer, it will start from 0 again. Yeah, so the whole thing will loop. That's the thing. So other stuff is pretty obvious, I guess. The buffer number from which we read the sample envelope, buffer number. -1 for the node ID means that I don't care about the node ID, and the server will use its internal, very cheap, as it stated, cheap method to assign IDs to new synthesis nodes. And add action is add to head, I guess, or not. 1, add to tail. Okay, add to tail doesn't matter here because nothing goes to the input of previous one. And what else? What else? What else do we have? Nothing. Let's take a listen. Yeah, by the way, synth with the method of grain does almost same thing. It's kind of cheap method. It's cheaper than using synth new. It does the same thing, -1 for the node ID, and constructs OSC message with some internal effective methods, yeah. But this approach is the most, probably I would say, most flexible and effective one from the CPU stress point. Okay, let's take a listen. I don't know how obvious it is, but with my headphones I can definitely say that there is a small jitter going on in this whole process. Let's take a listen at this example. Here is a periodic tone with 200 Hz played by impulse unit generator. And here is the same thing with our granular, that grain synth, and with the same frequency specified by the Interonset. If I wouldn't know what's happening, I wouldn't say probably anything, but let's make it even higher. This is impulse at 800 Hz, and this is our granular process. Now it's more obvious, yeah, that jitter in the signal. It's because of the actual result is not pretty accurate time-wise. And this is the thing that I have, for example, on other laptop, much more exaggerated, with a bit different hardware. Okay, this is more or less fine, yeah. We still can hear the sample. We can get all its musical qualities, of course, in electronic music context, yeah. If we would use something like that to transmit the live orchestral recording, that would be unacceptable. Unacceptable. Well, to a certain degree. Back in the days, people used to listen music from wax cylinders. But nevertheless, we can do much better than this, without much hassle. Yeah, why would we do it like that? What if we want to kind of overcome the problems, because this jitter might be even worse? What is the method to get at least to interesting musical result? Increase overlap. Increase overlap. Here's an example. Let's put it to 8. Okay. On other machine, I have another result. Actually, this jitter turns out into a phaser effect, and not a recursive delay line like phaser effect. This is more like that tape type of phasing, bad tape. If you ever listen to that, bad tape gives you those phasing effects, and it's closer to that one. As you can see, both methods give you lots of possibilities, yeah, since we can represent the signal, at least musically, in a meaningful fashion. We can then start playing with that signal and creating lots and lots of different artistically interesting sound objects, soundscapes, and so on. We kind of fall into the same reality with this second method as electronic musicians in 90s and late 80s felt. Yeah, felt, okay, you got me. What they got back then, samplers that are called lo-fi these days. Those samplers with the Nyquist frequencies lower than the content that used to be recorded with those devices. Yeah. So what the engineers and those musicians were kind of forced to do, moved them towards very interesting artistic results. Some of the effects that came from the limitations of those devices by these days are considered as, well, to a certain degree, classic methods of digital processing. Even though we don't have these limitations now, you can see that some plugin developers with digital instruments and effect processors imitate those old defects, because they couldn't do better. Yeah. So they tried to do it musically interesting, and the musicians then, when they had those devices, those were by the way pretty expensive ones compared to these days instruments. They then used that in a corresponding musical context, and at that time it brought something new into a table of listener. I remember those days. I was a teenager in the 90s, and when I listened to some of those electronic music, breakbeat based electronic music, hip hop and all that, I knew everything about mechanical instruments. I heard lots of those, of course, guitars, electronic guitars, rock music, and all this stuff. But this thing, I couldn't figure out what the fuck is happening there. It's, how do they do that? I mean, what is this? How to get that sound? I mean, that was a mystery to me until, well, I got my hands dirty with that stuff. So it was interesting, definitely interesting. And with this second method, with this messaging based method, we, in a certain degree, following the same situation. But our methods are much more different and more rich than those were back in the days. So the next videos I will start from this GrainBuf thing, and we'll show how to, we'll show some of my recipes, what I would do and what is possible with this unit generator in the context of spatial processing, and not only. And also I will do some stuff with this approach, and from time to time I will adapt to this Microsound bunch of, I hope, rather short videos, new algorithms, because with this thing we can make a very long trip. So see you.